What is code? When we talk about software, we often get mired in conversations comparing one language with another or one framework with another. There do seem to be some differences between different programming languages in terms of productivity, but actually the results are so varied that I'm not really sure that we can trust these surveys. One says that scripting languages always win. Another recommends that Smalltalk is the most productive language of all, with C++, C# and Java and Python all coming second and scoring the same. But I'd like to take a look a little further under the covers. What is programming about anyway? What is it really that we do when we begin to wield whichever language we choose to solve problems with? Hi, I'm Dave Farley of Continuous Delivery. Welcome to my channel. If you haven't been here before, please do hit subscribe, and if you enjoy the content today, hit like as well. Let's begin by dismissing the race for productivity. This is a really difficult thing to pin down. I think that there have been some significant steps in improving productivity, the step from assembler to higher level languages, maybe the addition of object orientation, maybe the addition of functional programming. All of these have had an impact. But there are nearly always in fairly specific or certain classes of problems and fail for others. Visual Basic introduced hordes of programmers to programming in the 1990s. It was derided by many existing professional programmers at the time, and we called out how it would go wrong, and it did. But for small, simple, form-like user interfaces for simple problems, it was extremely effective. You could draw a picture of your user interface and hang bits of code off events, all inside a visual editor that gave you access to a working version of your code as you built it. This was pretty effective in its time for simple programs. It started falling apart as people began to build more complex systems this way though. I think that this is because the programming model encouraged you to make some rather unpleasant compromises. Before we go any further, let me say thanks to our sponsors. We're fortunate to be sponsored by Equal Experts, Tricentis, Transfic and Roost. All these companies offer products and services that are well aligned with the topics that we discuss on this channel every week. This channel wouldn't be able to continue without their support. So if you're looking for excellence in continuous delivery and software engineering, please do click on the links in the description below to check them out and recognize that support. Visual Basic demoed extremely well because it was very visual. You started by drawing pictures of your user interface. Non-programmers loved this. After all, the UI is all there is, right? Well, no, not for more complex systems anyway. This development approach started with you focusing primarily on the UI rather than on the problem that you were trying to solve. And as a result, very often, the implementations ended up as tangled balls of mud with no real structure, and with bits and pieces of repeated logic all over the place. This isn't too bad as long as the problems are very, very simple. But as soon as the problems begin to grow, the complexity quickly gets out of hand and systems built like this become unmaintainable. We can't change them anymore without being terrified of breaking things or making things behave inconsistently in different parts of the application. This was very common in Visual Basic applications as they grew, but I'm not only talking about Visual Basic here. This is also a common problem with low-code and no-code solutions, and many teams' use of other general-purpose languages and frameworks too. You can probably think of Visual Basic as a kind of early attempt at low-code systems, I suppose. The problem here is that we try to make software development seem easier than it really is. Visual Basic was designed and was very successful at being easy to learn. But while it made the easy to learn stuff easy, it made the hard stuff more difficult to learn. Good software development is profoundly about maintaining our ability to change things, whatever the technology. The alternative is that we have to get everything perfect the first time. This is not only unlikely, this is impossible in reality. Stuff changes that is outside of our control, and our understanding of the problems that we are working on evolves constantly as we learn more about them. What this means is that we need to add some sort of structure to our work, to our code, that maintains our ability to change it easily. What that means in turn is that the code is about much more than a simple sequence of steps. When I was head of software development at LMAX, I used to do all of the final interviews for technical development candidates, along with my friend and then CTO at LMAX, Martin Thompson. One of our common complaints about candidates that didn't make it was that they were what we called straight line thinkers. Straight line thinkers to us meant that the person had little or sometimes no obvious sense of design. They would think of solutions as a simple and sometimes less than simple sequence of steps. The end result of this style of thinking and approach to coding is the kind of tactical crap that leads to big ball of mud legacy systems. Seeing this from the outside in, it looks to me rather like being wholly in the moment. What code do I write that's the least work for me right now? And that's a very poor criteria for decision making in code. Let's imagine that I have this button on my web page and I want to write some code that stores new things in my database. I've just drawn the button on my page, so that's what's at the forefront of my mind. That's where I am in the code right now. So the obvious next thing to do is to add the store of my things to the click event handler for the button. It's easy to write the code like this. This is easy to understand at this surface level of complexity at least. This is what Martin and I meant by straight line thinking. Right at this moment, this is the simplest way to make this change. But this is lazy decision making. And as I said, this is the route to big ball of mud legacy systems. What happens now if we have another page that lets us, I don't know, add more details to the thing that we added the first time? Now we read in the previously stored version of the thing and then we store it again with the new changes added. Now we have a different button. Remember, this is a different page. So okay, we once again add some code to store our modified thing in the click event handler for the new button. But that means that now we've got two different versions of code for storing things. What if they're inconsistent in some way? At this stage, they probably won't be, because this code is so simple. And we can probably remember that there are two copies of the code for storing things. So if we need to change one of them, we'll probably remember to change the other one and keep it in step as long as our code is simple. But our capacity to do this is very, very limited in scope and very limited in shelf life. What happens when we have 50 features of our system that exist in more than one place? What happens even if we only have 5? What happens if we return to this code after 3 months or a year later? Will we still remember all the different places that we need to keep in step? What if there's more than only me writing the code? I may remember all of the different places that I added, but I'm not going to know the ones that you added if I'm not aware of them. Can we really expect to hold all of this stuff in our heads all of the time? I'm sure that you'll agree with me that code like this has a very severe limit on it, how complex it can become. It really can't be much more than a trivial before it gets seriously out of hand. And this kind of naive approach only works if you're working alone, really. So now let's imagine that we need to add a new feature to the Add Thing page. This new feature lets us optionally create things with or without widgets. We go to the Add Thing page and change it to allow us to decide whether or not we want a widget. And we update our Store click event handler to create and store our things with widgets, if that's what we've selected, into the database. But we forget that we have a store code in other places too. So the next time somebody uses the update page, they read in things, but the code doesn't know about widgets now. So when they save things back out with any changes from this page, they don't save the widgets, because that version of the store knows nothing about them. Okay, that's a simple example. And sure, we could arrange things to be safer than that. But in deciding to arrange things to be safer, we're now designing rather than just coding. This fragility is exactly the kind of problem that happens, usually on a much bigger and more complex scale, when you don't worry about the design of your code. As I said in an earlier video, I think that the big step from junior developer to more than junior is that we are responsible for solving problems, not merely transcripting code from some detailed description of a design created by someone else. Design matters. Design is what our real job is. Design is how we organise our work to keep it understandable, navigable and maintainable, however complex the system becomes, and however long it is before we return to it. Design is also, at least for me, the joy, the real pleasure of software development. Sure, I love coding, but that's only because code is the means by which I record my design decisions. A significant part of this idea, this approach to development, is that to design things, we need some kind of organising principle in mind. There are some generic principles that I believe are fundamental to all software development, whatever its purpose and whatever its nature. But there are also team and context-specific organising principles that you need to decide on and adopt in your context. I've spoken a lot of times about what I think are the generic principles. These are what I call the principles that allow us to manage complexity. These ideas allow us to better understand our code and to change it easily and safely. My book, Modern Software Engineering, describes my thinking on each of these principles in some depth, along with 5 others that help us to optimise for learning, which is another cornerstone of software development alongside managing complexity. There's a link to that book in the description below if you'd like to check it out. I think that these ideas matter for a variety of reasons, but not least because if you only use these as your guiding principles for every design choice, you'd never build a big ball of mud. But there are other things that help too, though these other things are nearly always rather like emergent ideas that are built on top of these 5 foundations. In our silly example, we could, as a team, agree that we're going to have a rule. We don't allow data access in the layer of code that deals with the UI events. This is a simple step and would make us improve the separation of concerns in our design. And in that step, we'd also improve the modularity, cohesion and abstraction in our design too. Now, it's clearly more obvious that it would make sense to write the store things code once and then share it between all of the places where we needed to store things. With that simple design decision, we've quite dramatically improved our solution. We could take this further and decide that there is a core to our system that really represents the problem that we are trying to solve. In our example, the idea of things and widgets. So we could make the choice that we'd like to deal with those ideas without worrying too much about how they're being displayed or how they're stored. This is another form of separation of concerns where we separate the accidental complexity of running stuff on a computer, display and storage in this case, from the essential, whatever it is that makes things and widgets important to our users. Now we've ended up with that perennial design approach, the 3-layer system. We could take this further as our system becomes more complex, dividing our system into services focused on distinct, specific behaviours that matter to our users. Maybe having one part of the code that allowed us to build things and widgets, and another that allowed us to sell them, perhaps. So we'd want these things to interact with one another, but not be too tightly bound together. So we need to find an appropriate simple abstraction of the conversation between them and use that as the interface between them. This allows us then to change our code easily in one place without it affecting other parts of the system, allowing us to update the sales pages, maybe with special offers, without construction site needing to change at all, even without it needing to be aware of that changes happen on the sales page. All of these are design decisions and choices, and all of them are fundamental to what it is that we're being paid to do for a living, to produce software that's useful for people in some way. To do a decent job of this, we need some guide rails. We need to be able to reject stupid, expedient changes when they don't fit into our model of the system. Or we need to change our model of the system when it doesn't fit the new problems that we've now learned that we need to solve. In my opinion, it's never acceptable to write code just because this is the place where I found the problem, or because this is the place where somebody told me to fix it. Just because I could write code here and maybe fix the problem doesn't mean that that's the right thing to do, or that I've done a good job if I do that. Once again, this kind of tactical hacking is the road to really terrible code. I think that you should always have a mental model of the system that you are changing. Enough of a model to be able to tell the difference between a good place to fix something and a bad one. There's one exception that I can think of to this, and only one. And this is a corner case on a corner case. If our production system is broken and is bleeding money in production, well, first we should probably turn it off. But in this case, let's assume that we need to get the system back to working as quickly as possible. So if we really must, then we may need to do the simplest fix possible there and then, wherever we find a place where we think we can fix it. But even then, we still need a model to decide if our changes are going to break something else important. Also, importantly, if we do make this kind of tactical hack, we aren't done yet. What we've just done is put our finger in the dike to give ourselves a bit more time to think. If we leave the code like this, we should be rather ashamed of ourselves. We have to do a better job than that. So now, while the leak is stemmed, we go and have a look again for the real fix. If that means refactoring the code to make the fix better, and by better I mean leaving the code in a state that will make it easier to change in the future, then we must refactor the code and apply the fix to our new better code. But we do this immediately. There is nothing higher priority than this at this point, once our system is back up and running with our temporary hack finger in the dike solution. If we work in this way that keeps our code easy to change, this is much less likely to be a problem, because our code will already make the place where we need to fix the problem more obvious. This is what design is really for, to allow us to make good progress now while we're adding new features, and in the future when we're adding more features and maybe fixing problems that we didn't foresee. By having some opinion, some mental model of our system that we always use to evaluate our choices at the point when we're making them in the code, we have those guide rails that I spoke of. Does this change fit or not? Does this leave our code in a better state or worse? We must have some form of model of the code in our minds if we aim to steer away from the software entropy of big balls of mud. I think that the foundations of managing complexity are fundamental and generic. I think that isolating the accidental complexity from the essential complexity of our systems is a very good idea in general terms. I think that having the core logic of my system separate from all direct I/O is a good rule of thumb. And another is to have a layer of my own code that abstracts my use of any third-party code or frameworks, beyond the standard libraries anyway, will help me to keep my system easier to test and easier to change. Don't repeat yourself is a very good guideline in the right context, and ideas like tell don't ask, dependency injection, ports and adapters, services, layering, hexagonal architecture, and minimizing side effects and immutability can all help guide our work in the direction of better designed systems. But the fundamentals are the fundamentals. You can map all of these other ideas back to the real reason why they're useful. They all improve one or more of modularity, cohesion, separation of concerns, abstraction, and coupling. All of this is about design. This is more than only code syntax, though quite a lot of the more valuable aspects of code syntax are also about trying to help us enhance these fundamental properties in our code. I see no separation whatsoever between design and coding. Code is merely the mechanism that we use to capture our design decisions. Code, and for me at least, code alongside test-driven development, is the tool that we use to explore our design choices. But designing is what we are doing whenever we code. You may be making poor design choices, but you're still designing, even if only by accident. And I think that it pays to remember that code is always about design. With every line that you write, you're making a design decision of some kind. So having some model, any model that guides your design choices matters. I think that my 5 suggested things can operate in that capacity and give you a kind of fitness function for design. If we always choose the path in our designs that keeps our code easy to change, our code will be better because someday we will need to change it. But even if you disagree with that, you must have a model, else your design choice is chaos and the outcome is ever increasing entropy. Thank you very much for watching, and if you enjoy my stuff on the channel here, please do consider supporting our work by joining our Patreon community. There's lots of fascinating discussions in the Discord. Thank you.